Okay, today's problem comes from Serway Jewett's physics textbook. Oh, I can't even remember which edition it is. Not the most recent. I think it's the 9th edition. Problem 4.46 in their projectile motion chapter. And the adaptation is essentially, can a grounder in baseball reach its target catcher or player faster than throwing a straight shot? So a grounder means you're throwing the ball, but you're intending for it to hit the ground and bounce at least once before it gets to the player, as opposed to throwing it at a slightly higher trajectory and just getting it directly there. So this orange path here would be the direct path that takes you from where you are to wherever the player is that's trying to catch the ball. And then let's say that's some distance d away. And let's say that we're launching that at some angle phi, which will be a little high. Maybe it's 45 because you're trying to reach maximal range or something like that. Versus with the same speed, we assume people can throw at the same speed kind of in all directions. But at a lower angle, what if this red path is followed, the ball bounces once, and then let's assume that after the bounce, it's still going to come off at the same angle, but at a reduced speed. I mean, when you hit the ground, you're probably going to lose a little kinetic energy. It's not perfectly elastic. So let's say that the bouncing velocity, or rather the bouncing speed, is some fraction e times the initial speed. And that e is closely related to, but not exactly the same as, the coefficient of restitution. That we'll probably talk about in a different video. And the question is, can I compare the times of these two different trajectories, the orange versus the red? We'll look at this in general, and then we'll plug in some specific numbers to see what kind of edge, if any, might be gained from doing this. So first off, we know that this range for all three of these parabolas have nice formulas. Now that's the general range formula. I now want to adapt it for our three different parabolas here and use the variables we're given. So we know that the d, which is the whole range using the orange trajectory, will be v naught squared over over g sine of 2 phi. So phi is the launch angle for the orange. We also know that d1, which is the range of this first red trajectory, will be v naught squared over g sine 2 theta. And we know that d2, which is the range of this second one, will be v naught prime squared over g, but with the same angle theta. At least that's the assumption we're making. Now in reality, who says that's what has to happen? It could be that when it hits the ground, this angle becomes a little flatter or becomes steeper. It really would depend on some specifics of the friction with the ground, as well as how inelastic the ball is. So we'll just assume for now that the bounce angle is the same. Notice from the geometry, though, that d1 plus d2 equals capital D. So we get a nice equation here. Let's also go ahead and plug in v naught prime as e times v naught, just so we can cancel all of those common v naughts. So there's a v naught squared over g in every single term, and then these two can be kind of grouped together. Okay, so here's our result that tells us how these angles have to be related in order for it to actually cover the same distance. In other words, if we wanted to solve for theta, the angle at which you'd have to throw compared to your regular no bounce throw, we could do some inverse sine function. Okay, so let's save this off to the side, and then let's calculate the timing for these two different pieces, remembering our flight time formula. Okay, so we have a relation over there. This is the flight time for a projectile in uniform gravity. Let's go ahead and write down the total flight time. Maybe I'll call it T0, meaning no bounce. That'll just be 2 v naught sine phi over g. And then the total time of this second trajectory, maybe I'll call it T1 for one bounce, will be 2 copies of this for each of these two parabolas. Now, in reality, we're more interested in what the ratio of these two are, and that'll let us determine which one is faster or slower. Let's look at the one bounce time of flight to no bounce time of flight ratio. And we can see there's a common factor of 2 v naught over g in all of those. So canceling that out, we get a nice ratio, which when combined with this angular geometrical constraint that we found earlier, will let us figure out when this ratio may be larger than 1 or less than 1. Okay, so now to do something a little bit analytical, I guess, although it's really more numerical, let's go ahead and pick a specific value for E. Let's say that E is 1/2, meaning when this ball hits, half of its speed is lost. I'm not breaking that down into half of its vertical speed or half of its horizontal component of velocity. I'm saying half of the total speed. And we want that to be in such a way that this angle is maintained after bounce. So you can think about what that means for the two components. They probably both need to be reduced by like a √2 type thing. So now we need to plug this into this equation to find out what our theta is in terms of phi. Let's also assume that we're looking at comparing this to the maximal range throw. Let's say you're really far away and you want to throw to maximize your range, and we know that that happens at 45 degrees. So at this 45-degree angle, which would maximize this, what angle should we throw so that we get a little bounce, and does it get it there faster? Okay, so if we do that over here and solve for theta, we'll see that theta is just going to be 1/2 the inverse sine of sine 2 phi over 1 plus e squared. That's in general. In our particular case, since 45 gives us a sine of twice that being 1, and 1 plus 1/2 squared is going to end up being 1/4 squared plus 1, which is 5/4 in the denominator, we'll have 1/2 sine inverse of 4/5. That's about 26.6 degrees. Okay, so that's the angle that we should throw under these settings in order to get it to the same place. But now let's look at the time. So if I go plug that in with a 1/2 right here, a 45 right here, and this angle that we just found here, it turns out that this is about 0.949, which is less than 1. That means that the one bounce path takes less time than the no bounce path by about 5%. That's interesting, right? It means that throwing it with this grounder effect does actually get you there a little bit quicker than throwing it straight away. Not a lot, I mean, it's only 5%, but that's pretty impressive considering we've lost half of our speed in the bounce. You might think that you'd pay a big price for that, but apparently staying low makes that timing take a lot less, well, at least a little less. Now, we can ask about different ranges we might put here, so let's go ahead and write this down in its generality based on this, assuming that we have a 45-degree launch angle, but keeping E a variable. So now that sine 45 in the denominator will pick up a √2, and then we have the sine of this inverse sine stuff. The sine of 2 phi, though, is still going to be 1. So this is a pretty complicated function of E. I see the E out front is easy, but then this E squared in the denominator of an arc sine inside of a sine is ugly. There's probably some way to do some trig reduction here to maybe make this look a little more comfortable with roots and other algebraic functions, but I'm going to leave it like this right now. Our question is, when is this less than or equal to 1? Because those are the cases where the grounder will actually get you there faster. It turns out numerically that this is always true when E is greater than about 0.339. So as long as your elasticity, I don't know what we want to call this, it's not quite the coefficient of restitution, but as long as your rebounding speed is at least around 34% of what you landed with, it will actually be faster, at least at a 45-degree launch angle, to throw the ball in this grounder path. Now, if you start tweaking the launch angle, you'll see that this changes quite a bit. So for example, if you're not trying to throw it at max range and maybe they're closer than you think, and you're throwing it at a lower angle, decreasing this phi here and hiding in here does actually require you to push up your minimum value of your E in order to make up the time. So throwing it at a lower rate, or I should say at a lower angle, does need a little bit more elasticity in the ball. At any rate, we've seen that at least under fairly standard conditions, and actually kind of conservative ones, because an E equal to 1/2 that's a lot of speed loss, we can still arrange for the ball to arrive at our intended target a little bit faster than throwing it directly, even though we're taking a hit on that bounce. And this can probably be generalized to having more than one bounce. In fact, it definitely can. We'll have to make up some approximations for maybe the E should be the same on each bounce, or maybe we can start relaxing the issue of this angle being the same angle there. And with a little bit more analysis, we can actually figure out what that theta prime would be in terms of the actual coefficient of restitution and the kinetic friction coefficient of the ball against the ground. But for now, I think this is a pretty good, at least proof of concept that grounders can get you there faster. QED.